Hello, everyone. My name is Gabriele Liga, and I'm a research fellow in the ICT lab at the Eindhoven University of Technology. So before I start with my presentation today, I would like to acknowledge the work of my co-authors, Bin Chen, Astrid Barreiro, and Alex Alvarado. So as we know, the linear interference models are crucial both for the analysis and design of modern optical communication systems. The current models are able to capture the NLI power as a function of a variety of different system parameters, such as the transmitted power, transmission power, the reach, fiber parameters, and ultimately also the transmitted modulation format. Particularly, this dependence with respect to the transmitted modulation format is really important because it allows us to do constellation optimization in the optical fiber channel, which is so important as we don't know still what the ultimate shaping gain is in this channel. However, all the available models are only valid for polarization multiplex 2D formats. And that's why today I'm going to show you how we extended the previous models to also account for general dual polarization 4D constellations. But what is a dual polarization 4D constellation, or DP4D format? Well, a DP4D constellation is a discrete set of 4D points that are mapped into the 4 available dimensions of the optical field, meaning the 2 quadrature components on each of the 2 polarization channels, X and Y. A subset of the set of DP4D formats is the set of polarization multiplex 2D formats, or PM2D, which can be generated by simply doing a Cartesian product between so-called constituent 2D constellation by itself. An example of such a PM2D constellation is the well-known PM16 Quam constellation, for which the 4-dimensional points can be generated as using all possible combinations of the points of the 2 constituent constellations on X and Y. An interesting properties of PM2D constellation is the fact that they can be entirely described based on the constituent constellation in 2D, and that the constituent 2D symbols AX and Y can be regarded as independently identically distributed random variables. Here we are not interested in dual polarization. We are actually interested in dual polarization formats that are not polarization multiplex 2D formats. An example of such formats is the so-called 4D 2-amplitude 8 PSK modulation, which is given by these 2 projections in X and Y. And for this constellation, we actually introduce dependence between the 2 components on X and Y. And particularly for this 4D constellation, we can see that whenever we select the inner ring on the X polarization, we are only allowed to select points on the outer ring on the Y polarization, and the other way around. In general, for such DP4D formats, the AX and AY component symbols are neither identically or independently distributed. So what we did is we introduced a new model, a new expression to accurately capture the nonlinear interference power for general dual polarization 4D formats. And this is the expression that we obtained. And as you can see, there are 11 terms compared to the 3 terms that you would normally see in previous models, like the EGN model. And these terms, chi corresponds to multidimensional integrals. And these terms are coefficients that contain both intra-polarization moments and cross-polarization correlations of the 4D constellation. Among these 11 terms, we can see that these 4 terms can be attributed to the EGN term, so they are already appearing in the EGN model. And because we drop the assumption that the AX and AY symbols are IID, we obtain this additional 8 terms, and we also have, as a result of dropping this assumption, we also modify the original EGN coefficient. An example of such coefficients is this phi1, which is in our model given by this expression, which contains this cross-polarization correlation here. And whenever we use a PM2D, polarization multiplex 2D format, this term simply reduces to a constant 3/2. Let's have a look at the results, the numerical results for this model. So we first estimated the nonlinear coefficient vector eta, containing both the values of the eta x and eta y, so the two coefficients on the two polarizations. And we compared these values with the split-step Fourier method estimation of the nonlinear coefficient. And then we also use as a reference for the accuracy of our model and a heuristic extension of the EGN model that attempts to predict the NLI also for general DP4D formats by replacing the constituent 2D constellation moments with the two projective constellation of the 4D constellations of the 4D constellations that we want to analyze. So the system under consideration is the one described by this table. It's a single channel multi-span system, and we analyzed 5 different constellations here, different cardinalities. So the first one is C416, then the 4D 64 PRS constellation, the L428 constellation, the 4D 128 orthon symmetric, and then finally a polarization multiplex 64 QAM constellation. As we can observe, the heuristic extension of the EGN model that we here refer to as the 4D EGN model either overestimates or underestimates the true eta x in this case, so the nonlinear coefficient over the polarization x, and this depends on the actual constellation that we are trying to predict the NLI of. Also, the 4D EGN model shows a deviation of 0.8 dB from the SSFM estimates of the nonlinear coefficient for the constellation C416. On the other hand, our model, here shown by the blue bars, is always within 0.1 dB from the SSFM results. The same can be observed for the nonlinear interference coefficient over polarization y, and here the EGN model, the 4D EGN model, overestimates the true nonlinear coefficient estimated through SSFM simulations by up to 0.9 dB for the L428 constellation. And still our model is within 0.1 dB from SSFM for all constellations considered here. In order to provide a more comprehensive picture of the accuracy of our model, we looked into a wider range of 4D formats that we took from this very comprehensive online database of 4D constellations. And then we computed the average gap between the model and the SSFM results over the two polarizations. And here you can see a yellow line represents the results for the 4D EGN model. And the 4D EGN model on average can deviate from the true values of the NLI coefficient by up to 0.75 dB for constellation cardinality of 16. But for higher cardinalities, the gap reduces to within 0.5 dB. Still, our model on average is within 0.1 dB across all modulation formats included in this database. If we look at the worst case and best case scenarios, we can see instead that the EGM model can deviate from the true value of the nonlinear coefficient by up to 1.75 dB, again for cardinality 16 in 4 dimensions, whereas our model can only go up to a maximum deviation of 0.2 dB, still for a cardinality of 16. And finally, we looked at the most nonlinearly tolerant 4D constellations within the previously cited database. And again, here we can see the yellow line represents a result for the 4D EGN model. And there is clearly an offset, not just an offset for the 4D EGN model compared to the true values of the NLI coefficient estimated through the split-step Fourier method, but also these values don't seem to be fully correlated to the actual values obtained through the SSFM results. And this is because the deviation is actually dependent on the specific modulation format that is analyzed. On the other hand, our model shows nearly perfect agreement with the SSFM results. Another thing to note is that the maximum deviation of the EGM model for this average NLI coefficient is 0.75 dB. And another interesting observation that we found is the fact that for this 4D constellation called 120 Self-4 600, this constellation shows a pretty good nonlinear behavior, meaning it's a highly nonlinearly tolerant constellation, at least among all high cardinality 4-dimensional constellations considered. In conclusion, we introduced and assessed the accuracy of a novel model for the prediction of the nonlinear interference power for general dual polarization 4D formats. The new model extends previous models already available, which fail to accurately predict nonlinear interference for non-polarization multiplex 2D formats. And this results in a deviation of these models of up to 1.75 dB from SSFM results, but on average, the deviation is about 0.5 dB across the range of constellations that we considered here. Our model, on the other hand, is more or less always within 0.1 dB. And it just showed a peak deviation of 0.2 dB for a low cardinality modulation format. Extensions of this model to cross-channel nonlinear interference terms is currently under study, as we only provided a formula for the self-channel interference component. And finally, we believe that this model will be a key tool to optimize dual polarization 4D constellations in the optical fiber channel. This concludes my presentation. Thanks for watching. And of course, I'm here to take all your questions.